Kopman.
I'm Draak.
I'm Engholm.
And I'm Emma Hayhurst, and we are Senior Design Team 10 of the Biomedical Engineering Department. Today we'll be presenting our project titled Torque Test System for the Medical Robot Accessory, which is sponsored by Stryker. The goal of the project was to design, construct, and test an end-of-the-production line torque test system for the mixed handpiece, one of Stryker's devices. The system that we created must be repeatable, require low operator interference, and very efficient and fast, as well as be run via PLC program.
To start the test, the handpiece is placed in the fixture and connected to the dyno via a Lovejoy attachment. When we turn on the program, the clamp pushes down on the handpiece in order for it to stay in place. Then, the pneumatic cylinder will push the trigger to initiate the start of the test. For our system, we had to design multiple components along with purchasing other pieces from McMaster-Carr. We designed an adaptable fixture that would allow for multiple different versions of handpieces to be tested. We also designed and had constructed the base plate that the fixture sits on, along with a containment box for safety reasons. There is also a rail system in place if Stryker wanted to implement a second pneumatic cylinder in the future. All the automated features such as the clamp and pneumatic cylinder run according to the PLC program and an air supply. Each automated component has its own valve and tubing. Lastly, the blue box on the right is the dynamometer, which is sending the torque and speed values to a separate controller. As you can see, the controller is showing the torque being built up along with the speed of the handpiece.
Here we have the PLC program. To start the test, a switch will be flipped which sends power to the PLC hardware. The first section sets up all the timers for the clamp and cylinder. On rung 3, the clamp is activated. The next portion activates the cylinder, which then activates the trigger. Then it slowly ramps the brake torque up to 30 ounce-inches. Once the brake torque has been reached, the device is tested to see if it can maintain a speed of 12,000 RPMs for 3 seconds. The data is then moved to arrays to be analyzed. The data in the arrays is taken out and used to calculate the average speed of the test. The limit function is used to determine whether the average stayed between the upper and lower limits. If the speed stayed between these limits, then a passing test will be displayed. If the speed is too high or too low, then a failing test will be reported. After the test is finished, the speed array will be reset with zeros, and the cylinder and clamp will deactivate. Once the switch is flipped back off, the torque, average speed, and the torque counter will be reset. When the test is running, this screen will be displayed. When the test is finished, one of the following 3 screens will appear.
The challenges we overcame for this project were developing an adaptable fixture, learning and implementing PLC without any prior knowledge, using PLC to communicate between different devices and softwares, and moving past hardware defects and supply chain delays.
The team accomplished the goal of designing a torque test system for the mixed handpiece run via a PLC system. This included an adaptable fixture that stabilizes the device when the test is running, a containment box to fully enclose the system, a PLC program to run the system, and a display screen to display the results in an easy-to-read manner, as well as other features of automation to make the test faster and more efficient. The system is fully functional and ready to implement in Stryker's facilities.